Last class, we looked at the sinusoidal current conductor density distribution. So we had for any particular phase, NA of theta was, we derived this, how the term NT by 2 comes about, times sine of theta. And this would be, in a case of an ideal motor, we want the conductor density to vary continuously. That is not practical in a real motor. So what we do is we have finite number of slots. And for any slots, how do we determine the number of conductors? We basically integrate this NA of theta over the angle the slot sweep. Right? So if you take this particular slot, figure out the angle it sweeps. Right? So integrate from the lower bound of the angle to the upper bound. So I take any particular slot, the lower bound of the angle to the upper bound of the angle, integrate this density function, and that will be the number of conductors you put in the slot. Right? And if you get a negative number in that integration, you basically have a conductor go into the slot. If you get a positive number, you get a conductor coming out of the slot. So if you take for this example, we have +2. So we have one conductor coming out of the slot, going 180 degree outwards to the other side, and then going into the slot, and then coming out and doing this twice. And then the same wire goes to the next slot, does this, whatever the number of times the value this comes out to, and then we keep on doing it until we come back to the final slot. So we start off from the first slot, and we'll call this a terminal or something, and wherever we end, that we'll call as the neutral terminal. In case of a DC motor, the windings closed on themselves. In case of an AC motor, it doesn't. You'll start with one winding comes out, and a separate terminal will come out. But what they do is when they wind the other two faces, those again would have a B phase and a neutral wire, C phase and a neutral wire. If your load is, if your winding is all balanced and you have balanced voltages, then the current will also be balanced. That means the sum of the three currents will be zero. So if you connect all the neutrals, so you'll have A phase, and then similarly you'll have some terminal for B phase and its own return neutral, and then C phase and its own return neutral. So all these neutrals will be tied up together, because some of the three currents would have to be zero in the balance case. So why even bring the terminal out? So the motor manufacturer will just wind all of these, connect all the neutrals together and bury it in the motor. You won't typically get it out. Some motors do bring those out. If you requested, they will be able to bring that out as well if you need it. Okay. So then we looked at what will happen if we have this one winding in the motor, just one particular phase, and we pass some current, let's say a constant current of 1 ampere, and that current comes out. So we have some current source, and we are pumping a current into this with just one phase. And we saw how the H field in the air gap varies, right? H field will be maximum where the conductor density is minimum. That's what is indicated here. And again, the convention used in the chart here is from rotor to stator is considered negative. Stator to rotor is considered positive. So this is negative, and this is positive. In the exam assignment, I don't care which convention you choose, just let clearly mark what convention you have chosen. Right? And at the vertical point, this is where the H field is at its lowest value in the air gap. What will be the H in the iron? Was it? Zero. Zero, perfect. So we are going to assume for all of this course, we will assume the permeability of iron is infinite, that it never saturates, there is no saturation at all, and it's always infinite permeability, so no MMS drop the iron. So H in this iron is zero. What will be the B in the iron? Will there also be zero? If I give you the plot of H in the air gap, let's start with a simple one. What will the B look in the air gap? B in the air gap look like? What is the relationship between magnetic field and magnetic field intensity? Okay.
U naught mu r times h.
Perfect. So B is mu naught mu r times h. In case of the air gap, that mu r is just 1. So the B is going to have the same shape as what the H waveform is in the air gap. Right? It's going to be scaled by some magnitude, 4 pi into 10 to the minus 7 for the mu naught. Mu r is itself is 1. How about in the iron? In the iron, mu r I said is infinite. H is 0. So we have run into a bit of a problem. What will it be? What else can we use to figure out the B in the iron? Then we go back to our relationship that flux entering a surface must be the same, of a closed surface on one side must be the same as the flux leaving the closed surface on the other side. So if we go back to our diagram here, let's say in this cross section, we want to figure out what the B in the iron core is going to be. Whatever flux is coming out and going into the air gap must be the same flux coming in from the iron, right? The B needn't be the same in the iron and the air gap. B, in fact, will not be the same. Because if you look at the cross-sectional area here itself, we have a larger area for the air in the air gap, while here there are in between conductors through which the B field is not passing. It's only through these teeth that the B field can pass through. So the flux is the same, but the pathway for the flux to flow through is smaller in the ion near the teeth region. All right, so the B field will be different in the ion compared to the air gap, but the B field will not be zero. It will be a non-zero entity. Right? Okay, so this is what the H field looks like as well as the B field looks like in the air gap, just scaled by, so B in the air gap is just going to be mu naught times H in the air gap. And then we can figure out exactly what it looks like at every single point for a particular given instant of time. And then we can do the same for B phase, and we can do the same for C phase. It is just that the B phase and the C phase conductor density are just shifted by 120 degree. It's as if we wound the motor and shifted the whole thing by 120 degree pretty much, right? And then the same thing for C phase as well. And when you have all of these three windings and you somehow pass same current into all of them, which is not possible in a three-wire system, you would get these H fields which all look the same, phase shifted by 120. The net H field is basically sum of these H field at any given single point. So if you sum of this, and this, you'll get zero. If you sum of this, and this, you'll get zero. Every single point will sum up to zero. Okay. And then next what we saw what will happen if instead of giving a constant current into this phase winding, we start to vary the current at the phase winding in a sinusoidal manner as well. So previously our H expression was just H equal to NT I divided by 2Lg times cos of theta. So it was just varying as in spatial angle alone was the one determining. Now we are going to replace this current I with Im cos omega t. So what that means is at any given instant of time, the current is some value, and then some other time later it's increasing and increasing or reducing depending on which way the current is going. So as the current changes in this plot here, you can see that the B field, the H field and the B field effectively in the air gap just shrinks and increases, goes up and down. And we notice that this is the same as the standing wave that you have seen in the physics experiment when we do sound speed estimation. And there we have a forward traveling wave and a reverse traveling reflected wave which interfere to create a standing wave. In our case, we are doing the reverse. We do have a standing wave in the air gap. We recover a separate mathematical forward traveling wave and a reverse traveling wave just to pure mathematical operation. So that's the equation that I've written down here on the board, and once I lift the screen, you'll see the rest of the equations for those. Right? So we have a backward traveling wave. Those of you who are viewing this video later, the orange color waveform doesn't show up clearly. It's not even visible. So, but that is there though. Just look very closely. So, and then we have this purple color waveform, which is traveling in the other direction. The average of it will be the black waveform, which is just going up and down, right? So this is only for one phase. And then again, here just a bit clear what's happening. So when we have all three phases, we would have the rotating fields of A phase, B phase, and C phase in one direction, and there are other rotating fields of A phase, B phase, C phase in the other direction. And our math shows that in one direction, the fields are all pointed at the same direction at any given time. In the other direction, they are phase shifted by 120 degree. So the negative sequence components cancels out and the positive remains. If you are passing currents in the sequence IA goes to IA, IB goes to IB, and IC goes to IC, or time cos omega t goes to IA, cos omega t minus 2 pi by 3 goes to IB, cos omega t minus 4 pi by 3 goes to IC. If you flip any of these sequence, if you swap A and B, or B and C, or C and A, you would end up with motor going in the other direction, because the sequence that gets cancelled would be the positive sequence and you'll be left holding on with the negative sequence, so the magnet would travel in the opposite direction if you were to drop a magnet for the rotor there, right? So that's how you would reverse. So if you do two swaps, let's say I have A, B, C is the sequence. So here in your wall outlet, let's say you have three terminals marked A phase, B phase, C phase, and you connect your motor A phase, B phase, C phase exactly to the correct terminals, then let it rotate in one direction. If let's say this is the direction it rotates, all I have to do is swap B and A, then it would rotate in the opposite direction. If I do one more swap, BCA, it would go back to the original rotation again, right? So it's a singular swap. If you do twice to two swap, you again go to the same original rotation. It is just the initial starting angle would be different depending on the rotation that you do. Okay, right? And then here's basically when you have all of these three sinusoidally phase shifted currents going into windings that are physically phase shifted by 120 degree, you end up with this net wave which travels in just one direction, while each of the individual waves of the H field vary up and down, but the net wave is always going to be going in one direction. So if the peak of any one single value is, let's say, H peak, then the net would be H peak times 3 by 2, right? Okay, does anyone have any questions? up to this part? So this is all the rotating field theory is. So far, we are only considering just getting an intuitive feel for what's going on. We'll derive a detailed math of all the torque prediction and the reluctance and everything later. But this is just to get an understanding. Okay, so next what we're going to be looking at is let's do the polyphase thing. Okay, so we have so far we have looked at the three-phase case. I said that even in a two-phase motor, you do get rotating fields and the motor will rotate. In a one-phase case, clearly it won't rotate because we already saw one-phase case. When we just looked at one winding, A-phase winding alone, we got the standing wave and that's not going to rotate a magnet. We've already seen the case. So in case of a three-phase, this is the situation. In case of a two-phase motor, how do I order the winding? In case of a one-phase, three-phase motor, I ordered it as 360 divided by 3, right? So every winding was phase shifted by 120 degrees. In case of a two-phase motor, how do I, where, let's say my first coil is in A phase, where will my second coil be?
90 degrees away.
90 degree. Anybody had 180 as an answer? Why? Okay. Those of you who said 90 degree, why can't we do 180 degrees? Why do we put it at 90 degree?
180 would just be inverted,
Perfect. Which would be same as
just like doubling the amplitude
of
of the initial.
one phase motor.
Yeah.
Right? So if you had a coil at 0 degree and another coil at 180 degree, right? So here you see the two waveforms. So I have current, I don't know if it's visible. Oh, it's pretty visible. So you have the red waveform is the current going in the A phase. So let me call this A phase and let me call this B phase. And the green is the current going in the B phase, which is 180 degree phase shifted. But if you look at the flux that comes out on the top, you see the green one. The red one is basically lying underneath it. When I wrote the code for the plotting the red and the green just overrode the red line, but it's basically right underneath it. So the sum of the green and the red that are exactly the same is basically giving you the double amplitude in the H field. All right, so that's all is happening over there. So if you put a coil on the opposite side, you end up with same standing wave in effect. So this is same as saying that I could have just put this dot here as positive conductor going into the page, the green ones. I could have just swapped it out with conductor coming out of the page and pass the current, green current in the same phase as the red current, right? The effect is the same. So it's just as putting two parallel one-phase coils. So when you have even phases, so when you go to a six-phase motor, for instance, there are two options as to how you'll put the winding. So you can do 60 degrees, 120 degree, 180 degree, 240 degree, and then 300 degrees. This would be exactly same as a three-phase motor because whatever coil is here and whatever coil is here, it will behave exactly what is happening in this case. So this will put a current like this in this direction. This will put a current exactly 180 degree phase shifted, and the flux would just be additive, not creating any rotational component. It will just go up and down, up and down. So this in effect would effectively be a three-phase motor. So when they wind the six-phase, this is also used because you can parallel the currents coming out of an inverter leg. So you have an inverter switch rated for, let's say, 100 ampere, but your motor is going to have to run for 200 amperes. Then you can do basically put 100 ampere on this leg, 100 ampere on this leg, basically paralleling the winding. So you get 200 amperes effectively going into the motor without stressing out on the inverter as well. So there are advantages to doing it. But typically the way we'll wind this, if we had a six-phase motor, would be the first coil would be here. The second coil will be 30 degree phase shifted, right? And then the third coil will be here, and the fourth coil will be 120 plus 30, 150 degree. And then you'll have it at 240 degree, and then the other coil will be at 270 degrees. 240, 150, 120, 30, and 0 degree, right? So this would also, both of these configurations are there are six-phase motors. The first one would be symmetric grouping, the other one would be asymmetric grouping. But the second one, where I've drawn it in green, you get the advantage of some torque cancellations, that you get harmonic cancellation. Because the H field we saw, it's not a pure sine wave. It had those step values. And when you do FFT, you can reduce it into harmonic components. And when you have these asymmetric configurations, you can cancel out some of those harmonic components, right? So that's the advantage of doing that, okay? So in a two-phase motor, you would put the winding at 90 degree. And the minute you put the winding at 90 degree, you can clearly see two different components, right? The green and the red are two separate entities now. They are not lying on top of each other. And the currents are as well phase shifted by 90 degree. And then the net sum of those two would be a wave that's traveling in the forward direction, right? And the magnitude of that wave, the peak magnitude of any phase is, say, H peak. Then the net sum, let's say this is H peak. then the peak of the traveling wave would also be the same thing, h peak, right? Can you really give me a general formula for any polyphase motor? What will be the peak of the h in the air gap? So if I had a two-phase motor, 90-degree phase shifted, the peak h in the air gap was just h. If I had a three-phase motor, it was 3/2. For any polyphase motor, n. What will it come out to?
Would it just be the number of phases divided by 2 times the peak more of the waves?
Perfect. So if you go back to our case of a 15-phase motor, the peak here, I've scaled it, I put a tiny note there, but the scaled value is what is shown here. This would be h peak times 15 divided by 2. So each of these values, whatever the h peak is, the total sum of those peaks would be h peak times 15 divided by 2. Right? Again, when you have 15-phase motor, you have multiple options. You can take 360 degrees, divide by 15 and spread the windings evenly. Or you could do groupings of 3 and 5. Here I've done groupings of 3, 5. Or you can have groupings of 5, 3. So there are too many options in which you can wind these motors. And each of it has different harmonic cancellations that you can achieve depending on how you wind them. Right? Any questions? Okay. So any polyphase motor, any phase greater than 1, the motor will start rotating. Right? That's the idea that you need to take from this. Okay, so let's go to space vectors. Before I do that, there are those equations showing the h and the air gap. As you flip the current around, swap the current from B and C phase, the rotation changes. So you had negative omega t. But if I make B phase minus 4 pi by 3 instead of minus 2 pi by 3 and then C as minus 2 pi by 3 swapping the terminals when we connect to the grid, then the direction also reverses. Okay. Can I directly connect the permanent magnet synchronous motor to the grid? We did see this when we did the demo of permanent magnet synchronous motors. Has anybody done the permanent magnet experiment in the lab yet? Nobody. Okay. So I'll ask you this question again next week once you've done the experiment. Okay, so we have going forward, I'm not going to be drawing all of those windings. So instead, I'm just going to represent them as a coil. And when I draw this diagram, this means that there is a sinusoidally distributed winding representing this one. And the peak density of that winding is here, but the peak magnetic field of that winding is along this direction. So I'm drawing the solenoid diagram exactly where the magnetic field of that particular phase would be at its peak. And then I have the peak of B phase here, and then the peak of C phase here. Okay, whether you draw the B phase here or B phase there, that's totally up to you. Completely random. Okay. So every time I need to analyze this motor, it kind of becomes tedious to keep writing 3 different H fields, right, in this numerical way, and then sum them up. So what I'm going to instead do is let me give you the equation, and then we look at what it is effectively saying. So H net, I'm going to call it HA. E power J0, HB, E power J 2 pi by 3, plus HC, E power J 4 pi by 3. So we go back and look at our HA expression of theta comma T. There was some value NT IM divided by 2LG times cos omega T times cos of theta. Now, none of these information is necessary to be given. Right? All I need to tell you is the magnitude of the H in the air gap, the peak magnitude. And then you can fill in the rest of the components. It's always going to be cos omega T times cos of theta, because you're always going to assume A phase is starting at 0 degree, the H field for the A phase peak, and then it's going to split around, or the current density at 0 is 0 degree is 0. And then we're going to, then the B phase is going to be 120 degree phase shifted, C phase is going to be 240 degree phase shifted. So this information is somewhat redundant. If I tell you this value, you can figure out what this value is going to be, right, for all 3 phases. This again is a redundant information. Because if all I have to tell you is that current at time t equal to 0, the current is in the A phase is the maximum. Then you know 2 pi by 3 degrees later, the B phase current is going to be at its maximum. And then 2 pi by 3 degrees later, C phase current is going to be at this maximum. So again, we have too much information that's being provided here. This again is not necessary. But the one thing that I need to provide is the maximum value. And then you can figure out what the HA of theta comma T is going to be for A phase, B phase, and C phase all on your own. So what we are going to be looking at is going forward, we are going to only analyze what the H in the air gap at this particular location is at. So we are only interested in HA of 0, comma T, right? So that's what my HA here is. And then HB is going to be HB of whatever its peak at its own angle is, and HC at 4 pi by 3 comma T. Right, so we're only going to look at what the H field for the A phase is at its own peak angle, what the H at B phase is going to be at its own peak angle, and what H at C phase is going to be for its own peak angle. Right? And then we are going to plug it into this and sum them up. So what we are doing is we are taking a vector, we are representing the H in the air gap as a vector. So we have HA vector, we have some HB vector, and some HC vector. So at this particular direction, this is the value of HA. At this particular direction, this will be the value of HB. And this particular direction, this will be the value of HC. Right? And once, what am I doing in this portion? I'm taking the magnitude, multiplying with e power j0. That's basically indicating the vector along this direction. Right? E power j0 is just a unit vector pointing at angle 0 degree. E power j 2 pi by 3 is a unit vector pointing along angle 2 pi by 3. And e power j 4 pi by 3 is a unit vector pointing along angle 4 pi by 3. So if I take the magnitudes, multiply by each of these vectors, I just get a vector over the direction 2 pi by 3 and e power j 4 pi by 3. Let's plug in some values and see what this yields, right? So when I do this sum, let's just plug in some values and see what it actually gives us. And then let's see if this H net that I've defined here somehow relates to this H net of theta comma T that I've written here, right? So let's take some values. Let's say at time t equal to 0, you plug in these values. So you're going to get maximum. So let me call this term some value k, some constant. So HA is going to be, which is equal to HA at angle 0 degree at time t. And in our case, time t, we are going to substitute at time t equal to 0. We are going to get some value k. All right. So that's the value we get because this term is 1, this term is 1. And we have our vector. It's just going to be 1 k times e power j0. Okay. So same time t equal to 0, let's compute what HB is going to be. It's going to be HB, comma, at the angle 2 pi by 3, time t equal to 0. So let's substitute the value there in the HB expression which I have from there. So my HB of theta comma t was equal to k times cos omega t minus 2 pi by 3 times cos of theta minus 2 pi by 3. So what is my theta? My theta is 2 pi by 3. So this term is 0. This cos of 0 is 1. This term right here is going to be omega t is 0, right? At time t equal to 0, you substitute that. You end up with cos of negative 2 pi by 3, which is same as cos of 2 pi by 3, which would be just negative half, right? So we have HB is going to be negative k divided by 2. Now let me do the same for HC. HC of, again I'm interested in 4 pi by 3, comma 0, at just particular time t equal to 0. If I substitute those values, I would end up with k times cos of, instead of 2 pi by 3, it's going to be 4 pi by 3. And then this term is going to be always 0. So that's just going to be 1 there, cos of 0. right? So we have k times cos of 4 pi by 3, which is again equal to minus k by 2. So HC is going to be equal to minus k by 2. So let's plug them into this expression. So I've gotten the HA magnitude, HB magnitude, HC magnitude at a particular given time. So what are these values actually indicating? These indicates when I drew the H field in the air gap, right? This was the H field in the air gap for A phase, HA of theta at one particular time T naught, something. And then for B phase, it would have been phase shifted by 120 degree, but the magnitude will also be slightly lower. Okay? Because this was HB of theta comma T naught. This phase shift is indicated by this theta factor. And this time factor, because in cos omega T, the A phase, when it's at maximum, the B phase current magnitude will be lower. Right? It will be negative half of whatever the A phase current magnitude is. That is the B phase. And then my C phase would have been 240 degree phase shifted. This would have been HC of theta comma T naught, but its magnitude also reduced. Okay. What will be the sum of these three? Will it be 0? How many of you say 0? How many of you say non-zero? This can't be 0, right? If the magnitude of this and this was the same as this, it would have been 0. If the sum of these three are 0, then we don't have any H field in the air gap. That would be the case if all the three currents in the three phases were the same. But we are not doing that. We are passing different currents. We are passing cos omega t in the A phase, cos omega t minus 2 pi by 3 in the B phase, cos omega t minus 4 pi by 3 in the C phase. When we did that, we created a rotating magnetic field in the air gap, a non-zero rotating magnetic field, right? If I had drawn this blue waveform as the same magnitude height as the A waveform, and the purple also has the same magnitude height as the black waveform, then the sum of the three would have been 0, because I passed same current in all the three phase windings, which I know would not create any magnetic field in the air gap. Okay? So this would definitely not be 0. So what I have drawn here, what I have computed here, that is basically at any given time, t equal to t naught, what the maximum H along the A phase axis is, what the maximum H along the B phase axis is, that is negative k divided by 2, and what the maximum H along the C phase. I should have drawn this the other way around. You plug it in the equation, you will get it in the reverse direction. So what we are plotting there at 120 degree, what is the value of the B phase, and at 240 degree, what the value of the C phase is, 240 plus whatever the angle. Okay. Right, so those are the values that I plotted here. So the A phase peak at 0 degree angle, the B phase peak at 120 degree angle, and the C phase peak at 240 degree angle. And then let's sum these up using this vector notation that I have. So my A phase is some vector k divided by 2 times e power j0. Where will I draw the B phase vector? For these particular values. Where will the B phase vector come about when I do HB times e power j2 pi by 3? Where do I draw that? Would it be along this direction? Yeah, if it was also positive k, then it would have been along these directions, right? Because our vector itself is e power j2 pi by 3. We are multiplying it by a value of negative k by 2. So the vector would come out here, right? So this would be k times e power j0 for A phase, k divided by 2 times e power j. This angle is going to be 60 degrees, negative pi by 3. E power negative j 5 by 3. So this is the same as saying negative k by 2 times e power j 2 pi by 3. right? If I had a vector of negative magnitude along this direction, that is same as saying the vector is along this direction with a positive magnitude, just 180 degree in the opposite direction. So you typically don't want to put negative values on your vector, you would want to take it to the angles. So whatever the negative sign is here, I'm just taking it to the angle, which is same as saying I'm multiplying it by. So this is same as saying it's k times k divided by 2 times e power j 180 degree, right? This is -1 times e power j 2 pi by 3, e power j pi. So however you do it, you'll end up with e power negative j 2 pi by 3. Can somebody tell me where the vector for C will lie? Jinx.
Then also 180 degrees in the opposite direction.
The opposite direction, perfect. So C phase would just end up being k divided by 2 e power j pi by 3, because again negative in this vector, opposite direction would come up here. Now let's sum these three values together. We would end up getting k times 3 by 2 e power j0. Quite easy to see how that would come about, because if I resolve this, this does not have any y components all along this component. This vector, if I resolve it into the y-axis component and then the real component, the y-axis component would come out to be root of 3 by 2 times sine of 60 degrees times k times e power minus j pi by 3. Sorry, that's it. Right? Along the j-axis. And then this magnitude will come out to be 1 by 2 times sine of 60, cos of 60 degree, k divided by 2 times along the x-axis e power j0. Okay? So you would have had k by 4 for this. This again, when you project it onto the x-axis, you would get k by 4 plus k by 4 would be k by 2 added to this existing k. You would end up with 3 by 2 times k e power j0. What will happen to the vertical component? This vertical component would be along this direction. This vertical component will be along the other direction. Equal magnitude, they would cancel out. Right? So if you look at this 3 by 2 times k, we have matched it up with the h net expression that we have on the left there. So whatever k we defined here, it's the same k times 3 by 2. So that's exactly what we have here. And if you plug into the h net expression, time t equal to 0, right? At time t equal to 0, your h net expression would have been 3 by 2 times k times cos of theta right here. So at time t equal to 0, this would have been at time t equal to 0, this expression would have resolved to, so I'm calling this the term k for simplicity. So we have 3 by 2 times k times cos of theta. And where will this be maximum? At which angle would that vector be at its maximum? 0 degree. Right? At 0 degree is when the H field would have been at its maximum in the air gap or time t equal to 0. And if you look at the expression that I got 3 by 2 times k e j angle 0. Right? Exactly pointing to the angle where the H field is at its maximum. Let me do for some other angle now, because it could have just been a random one-off case where it just matched up. So let's do for one more case and see if it's really true. So let me do for 120 degree. Right? Well, let's do 120. So we have HA of theta equal to 0 at time t equal to omega t equal to, so at time omega t equal to 2 pi by 3. Right? So that's what we are going to be calculating it for. So if I substitute 2 pi by 3 here, I end up with same thing as before. This would become negative k by 2, right? And then HB, I'll have to calculate the peak of it at its own angle. And again, omega t equal to at the same instant in time. This would end up coming out to, if you look at the expression for HB, it is k times, where was HB? K times cos of omega t minus 2 pi by 3 times cos of theta minus 2 pi by 3. Theta I'm already substituting as 2 pi by 3, so that term, so let me write it down for clarity. So we have k times cos of omega t minus 2 pi by 3 times cos of theta minus 2 pi by 3. This I'm already substituting 2 pi by 3, so this term is just 1. And here if I substitute 2 pi by 3, this term is again 1. So I'm left with k for HB. For HC, do the substitution again. HC of 4 pi by 3, comma, omega t being equal to 2 pi by 3 again. That's the time instant. I'm sampling all the 3 H fields. individual H fields and then summing them up together, right? So this would again come out to, once you substitute and solve for it, you'll get these values. Now if I try to plot these vectors, so let me plot those vectors again. So HA e power J0, that would be, so this is e power J0, e power J2 pi by 3, e power J4 pi by 3. Now we have, let's do the simple one first. So we have HB is K times e power J2 pi by 3. Let's say that is coming out to be some vector like this. K times e power J2 pi by 3. Right? The next one, let's go to the A phase. If it was positive, then it would have been some vector K by 2 e power J0. Since it's negative, it will be in the opposite direction. Right? So that would come out to be half of this vector length, K divided by 2 times e power J pi. Right? Same as saying negative K divided by 2 e power J0. So this is HA times e power J0 for HA at angle 0 and omega t equal to at time, some particular time 2 pi by 3. When I say omega t equal to 2 pi by 3, or t is equal to 2 pi by 3 divided by whatever frequency we are considering the signal set. And then the same thing for this, where was the third one? Negative K by 2, e power J4 pi by 3. So again, it will be in the opposite direction. So this is going to be K divided by 2 e power J pi by 3, right? And this is going to be equal to HC e power J 4 pi by 3. And this itself was HB e power J 2 pi by 3. What will be the sum of this vector plus this vector plus this vector? If you had to take a guess,
3 halves.
what was it?
3 halves.
Could you repeat that? I can't hear you, sorry.
3 halves.
3 half and direction? Along e power
120.
120 degree. So because if you again resolve this component, you would have something, you can break this into two components, one along this and one perpendicular to this, right? Same thing you can do with this, one along this and one perpendicular to this. The perpendicular component of this and perpendicular component of this projection and this projection would cancel out. The horizontal projection along that vector would be a quarter again. You sum them up, you will get the same thing again. So H net, what you would get would be 3 by 2 times K times e power J2 pi by 3. Now let's go back to our H net expression here. At time t equal to, at time omega t equal to 2 pi by 3. What will the expression come out to? It will be 3 by 2 K times cos of omega t. Sorry. I'm doing it for this case. Omega t theta minus 2 pi by 3. The values I calculated is not without swapping it. Right? If I swapped it, this B and C should have been swapped around. Right? So the original equation is the one without swapping the B and C phase. So once I substitute omega t theta plus omega t, so I'm substituting for omega t as 2 pi by 3 here. So where will this expression be maximum? The H net at the bottom, where will it have its own maximum value by? 2 pi by 3. So at this given time, so what we are basically visualizing is where the peak H field is moving around. So this would be maximum, max H net will be at e power J 2 pi by 3 and its magnitude would be 3 by 2 times K. That's exactly what we got here. So you can do it for multiple different values. You can in homework I have asked you to derive it for a general case by basically substituting HA as this whole time varying component, HB as its own time varying component, HC as its own time varying component. You sum them up and solve this expression. That's part of your homework. You would end up with getting 3 by 2 times K times e power some j omega t. Maybe some you'll get some offset of pi by 2 or something depending on whether you consider cos or sine. Right? So what this is basically tracking, this whole expression that I have here, It's basically tracking the peak H field in the air gap as the current changes sinusoidally. Right, the whole H field that is rotating in space in our diagram here. So the H field that you see there, which is basically that purple waveform on the top. So the purple waveform on the top that is just going in the forward direction. The peak, if you see, it's moving in time. Right? So whatever expression that I wrote, the H net equal to some expression that we derived, that is basically just tracking where that field is going. So whatever is the H net that comes out at H 3 by 2 times K times E power J omega T, that is basically tracking where the peak is at any given time in the space. Right? So if I give you just that value alone, you can figure out every single other component. You can figure out what the A phase H field is, what the B phase H field is, what the C phase H field is, and I've already given you information of what the peak H field is. And then the rest of it is just varying sinusoidally in the air gap. Right? So that's the advantage of doing this procedure. And the equation that I wrote there, that's called space vectors. So the equation that I have here, this notation is called a space vector. It basically tracks where in space our current, too many cameras to juggle. So where in space our magnetic field is its peak at any given time. So at time t equal to 0, your H field will be at its peak at angle 0 degree. At some time, omega t equal to 2 pi by 3, your peak would move to this direction. At omega t equal to, let's say, let's do pi by 6 first. So at pi by 6, it will be here. At omega t 2 pi by 3, it will be along the b axis. At omega t being, let's say, pi, it will be along this axis, so on and so forth. Right? So this is where the peak H field is. How do I figure out what the H field? So let's say at time t equal to 0, peak H field is like this. What will be the H field at angle 0 degrees? At 90 degrees? So the peak H field at time t equal to 0 is along x-axis, along this direction. I'm asking you what will be the H field in the air gap at 90 degrees, not time t equal to 0, at theta equal to 90 degrees. For time t equal to 0. Leo? 0. Right? So all you needed is just one vector information. You can exactly tell me what the H field is going to be at every single point of the air gap just based off this one vector information at time t equal to 0. Now if I tell you at time t equal to pi by 6, the vector is along this direction, you can tell me exactly where the 0 is going to be. It's just going to be this value plus pi by 2. This is where the vector is going to be 0. What will be the values in between? It will be this peak vector times cos of omega t minus pi by 6. That's about it. Okay? So just this one vector information gives all the information that I need to draw the rest of the H field in the air gap. So in case of our B field, H field and all of these, that entity, that space vector has a physical meaning to it. But we are going to kind of extrapolate this further and talk about currents and voltages as well using the space vector notation. So what I'm going to be doing is I'm going to declare a new term, current space vector is IA e power j0 plus IB e power j2 pi by 3 plus IC e power j4 pi by 3. So again, in case of the H field and the B field is just mu naught times H net. Right? If you want to get B net, as long as the core isn't saturated, otherwise superposition itself doesn't apply in the first place. Mu naught times H net. And we are never going to consider saturation in this course, so don't worry about it. So in case of again the B, you can write space vector for that as well. And this indicates where the B field is at its maximum at any given time. And then the rest of the B fields in the air gap, you can just directly observe and infer from this single value that I give you. And now we are going to extend this for purely in a mathematical sense to currents and voltages. So I can define a voltage space vector as well as the voltage in the A phase times e power j0 plus voltage in the B phase times e power j2 pi by 3 plus voltage in the C phase times e power j4 pi by 3. A purely mathematical consideration, nothing more than that. But there is a problem. There could be a problem here. This current space vector has how many variables to it? How many variables do I need to represent that current space vector? Or how many numbers do I need to give to represent the current space vector?
3.
3. How many of you do 3? Anyone else? Any other answers?
6.
6. Any others? When I drew this, this was just a complex vector in a complex plane. Right, this was my vector, that's about it. So when I drew the H net space vector, all I needed was a value in the x-axis, value in the y-axis. Right, it's a complex number, it's some value, H magnitude, times some angle e power j theta. There are only two variables, the vector magnitude and the vector angle. That is all I need to represent the space vector. How many variables do I have here though? Those are actual current going into a motor, right? I have written those expressions right there on the left. IA is just some current cos omega t. IB is just some current cos omega t minus 2 pi by 3, cos omega t minus 4 pi by 3. So these are all real entities. Okay? These are all just some value at some particular given time. So these can have, let's say, 10 ampere. Let's say this is 4 ampere. What will IC be? Let's say IA is 10 ampere, IB is 4 ampere. What should IC be? Negative what? 14 amperes. So in this case, we do have three variables here. Are these three variables independent? No, because in our case, we have a requirement that IA plus IB plus IC must be equal to 0. In a balanced three-phase system, some of the currents, in a three-wire system, some of the currents have to be 0, whether the load is balanced or not. Some of the voltages would not have to be 0, but if there is, if these are balanced, then the sum will also be 0, VA plus VB plus VC. Right? So in a balanced system, these three variables are independent. So this has only two independent variables. This equation that I've written here has only two independent variables. So when I plug it into this and transform it into some other variable, as long as the independent variables are conserved, so here I have two independent variables. In the space vector domain also I have two independent variables, either the magnitude angle form or the x and y, real value, imaginary value form. Either way I have two independent variables that I can control. So going from this space to this space, I'm not losing any information. Right? That's very critical. If you have a case where you have your motor windings, and then there is a neutral which you have access to, and some of these three currents are not 0. Let's say this is not 0 coming out of this, then this would no longer apply. Alright, because you're having three variables on this side, three independent variables, because sum is not 0. You're mapping it onto two variables, then you're losing some kind of information. You can't recover, go from here back to this. But if you have this case where some of the three variables is 0, then you can go from here to the space vector and get the space vector back to your time domain values. Alright. So is this part clear? Any questions? Yeah, sure.
Just to clarify about, so H net, like the space vector, is a function of time and theta, right?
It's a function of time.
Just time?
Yeah, the theta will come out of the time.
Okay, so you can just like pick like that could be any angle where you're measuring H net.
Yeah, H net is basically pointing to the H field where it's maximum at any given time. Right, so given a time, the peak will be at one particular point. Right, it's not a sweep of all the values.
Okay, got it. Thank you.
Any other questions? Okay, so let's go back to our slides. Right, so what we have is, if all of these three variables are independent, our IA, IB, ICs are independent, let's say we have access to neutral and we can pass unbalanced currents, then I can choose any kind of three variables, right? And what three variables, if they are truly independent, they can occupy all the three-dimensional space, right? But we have our constraint in our case. In case of balanced system with balanced voltages, some of the three voltages will be 0. In case of a three-wire system, even if you have unbalanced voltages, some of the three currents would have to be 0. So those cases, if some of three things is 0, it represents what geometrically? If x plus y plus z equal to 0, what does it represent geometrically? It's an equation of a, if x plus y plus z is a constant, what is it? Equation of
Plane.
plane. So with this constraint that some of the three variables are equal to 0, it is just a plane, right? So that depending on those values, you would end up with if one of them is 0, the other two have to be positive, negative pairs, right? So this is a plane. So previously, if those three variables are independent, you'll occupy the whole 3D space. But with this added constraint, that some of the three variables are 0, you end up with a nice plane on which the points, all the currents and all the voltages of this balance system will lie. There is no other option. So that's how when I gave two values of current, Leo gave me the answer for the other current, or I don't know who gave the answer for the other current as 14 ampere, because all those values lie on the plane, because some of the three is going to be 0, right? So this is basically equation of a plane, and the space vector transformation that I wrote there, which is basically taking IA times e power j0 plus IB times e power j2 by 3 plus IC times e power j4 by 3. All that's doing is taking this plane and rotating it and showing it to you. That's all that equation is, right? So taking this equation, rotating it and showing to you. In a two-dimensional case, how do I do rotation? Those of you from computer science, what is a rotation matrix that you would use? Or even other people, you all done linear algebra. If I give you a two-dimensional vector in one particular xy plane and I ask you to rotate it to a different xy plane of some theta, what will be the rotational matrix you'll use? It's a very famous equation. So that would be your, whenever you're introduced to eigenvalues, eigenvectors, this is the first thing the instructor would have shown to blow your mind. Right? Because the idea is that eigenvectors will stretch vectors. Eigenvalues would basically stretch the vectors lying along the eigenvectors. But in this case, the rotational matrix, there is no vector you can choose that will only stretch the vector. It will always rotate the vector. Right? That's because the eigenvalues for these would be complex numbers. It'll just be e power j theta. So that's why you'll get a rotational aspect to it. You'll never give it a stretching concept to it. So eigenvalues, when they're real, you'll get stretching, but otherwise it's a little bit more complicated. So this is basically a transformation if you're doing a vector rotation in two-dimensional space. In our case, we have a plane in a 3D space and we are rotating it. So 3D rotational matrix is exactly same as a 1D rotational matrix. It is just that you will transform it in three-dimensional plane. So this is our equation. So this whole equation that I have here, so you first rotate along the z-axis, then you rotate along the y-axis, then you rotate along the x-axis. That's all we did in the previous operation. When we do this animation right here, all I did is ask MATLAB to confine these points to a plane, right? And that gave me all of these points. And then I just applied those three transformations that I showed. Rotate along one axis, rotate along the other axis, rotate along the third axis. And that's all it's doing here, right? So rotating along the three axes. And that's exactly the matrix that we have here. Rotate along the first axis, rotate along the second axis, rotate along the third axis by this particular angle. And that's effectively what this equation ends up doing on the top there, right? Anybody has any questions? Right, perfect. So we don't lose any information here because going from the three-dimensional space, we appear as if there are three variables, but there are actually only two independent variables, and we are conserving all the information. So once we go to space vector, we can directly come back to our time domain values, which we'll take a look at later. Pretty straightforward, it's just projection in the space vector to the particular axis that we are interested in. But the information is preserved there, right? But it has a nice short form notation because now we have to start visualizing all of these, right? We want to visualize how the B field varies in the air gap. And then once we go to induction motor, there'll be B field due to the stator, B field due to the rotor, how they interact with one another. There'll be some leakage fluxes going on. It becomes a very complicated picture if you have to think of B field spread across all of air gap. But now we made it very simple. When we talk about B field of the stator, it'll just be one vector, space vector that represents everything going on. And then we'll talk about another space vector for the rotor, and we'll just see how these two space vectors interact with one another. It's just a short form notation for the complex thing that's going on in the background, right? But the idea is we don't lose any information by doing this. Okay. And yeah, once you plug off all of those values, right, you plug theta x, theta y, theta z as this, cos inverse of 1 by root 3. This is the matrix you'll get. Right? If I break this down, what is it going to be? It's going to be VAN times cos of 0 degree plus VBN cos of 2 pi by 3 plus VCN cos of 4 pi by 3. And then there will be a J component plus J times VAN sine of 0 plus VBN sine of 2 pi by 3, VCN sine of 4 pi by 3. That's exactly what I have here. So I have this X times sine of 0, Y times sine of 4 pi by 3, Z times sine of 2 pi by 3, and then X times cos of 0, Y times cos of 4 pi by 3, Z times cos of 2 pi by 3. Right? So exact same expression that I have there. you'll get the exact same form. It's just I'm representing in a condensed form using the Euler's formula. Okay. Maybe any questions? Okay. So since we have a little bit of time, let's get a jump start on the PMAC. Okay. All right, so this is the diagram we have already seen. We have our three-phase motor. The whole B field is rotating, and the space vector that I just drew, that is basically capturing where this peak is. And if you see, Jonah, this answers your question. At any given time, the peak keeps moving. So space vector is basically capturing that peak. Right? So it doesn't have theta information as such. The time is the theta information that is being captured. So this is what the H field will look like for if we had just one phase alone, HA of theta at any particular given time. Well, can you tell me, guess what it will look like if I increase the number of poles? Let's say this is a two-pole motor. Because if you look at the H field, there is H field coming out, H field going in. So I can call this the north phase, this the south phase. So effectively, it just represents a two-pole motor, right? If I were to make it a four-pole motor, how will I, if I gave you this diagram and said I want to redo it in such a way that I have 4 poles in the system, anybody want to take a guess how will you go about doing it? Yep, Maxwell.
Have it distributed so that there's kind of 4 maximum parts instead of just 2 of the.
Perfect. So what we can do is instead of having exactly the answer Maxwell gave, so whatever motor I have here, if you see the conductors on the top half, 0 from 180 degree, were all positive conductors. And on the bottom half, it was all negative conductors. So think of it as cutting this motor open at this point and compressing in such a way that it only occupies 180 degree. Right now it goes from 0 all the way to 360 degree, but cut this motor here and just compress this so that it only goes from 0 to 180 degree. So whatever winding was previously the positive winding going from 0 to 180 degree would now lie between 0 to 90 degree. And then what happens for the rest portion? The negative windings were occupied 0 to 360 degree. Now it will just occupy the region between 90 degree to 180 degree. Right? So that's what we have done here. So quarter of the windings are coming out of the page. Other quarter of the windings are going into the page. Going into the page, coming out of the page. This in itself is a full motor. Right? And then we are going to repeat the same thing. We have conductors coming out of the page for the other quarter. Conductors going into the page for the other quarter. Right? So we have effectively created 2 motors. So we take the top portion and put it again on the bottom. We have effectively created 4-pole motor. Right? Everybody clear? Okay. So if you look at the H field for this, we can now again go back to this H field and say, hey, if I condense the whole motor, it's basically taking this H field and condensing it again into the half region. Or we can do the whole process all over again. We can take a loop here, analyze it. There is no H field. Take a bigger loop. H field increases. I can take an even bigger loop. H field is further higher. I can take an even bigger loop and H field is its maximum. And I can do the same for the other side. Take this loop. H field is negative, 0. Take this loop, which is integral H dot here will be negative. Take another bigger loop, will be even more negative. And then another bigger loop will be even more. So this will be the point where the H field will be maximum. And then when you go to this other positive winding, it will again do the same thing where H will be maximum at this point. Right? So you get 2 maximas for the H field and 2 minimas, basically going from the stator to the rotor. Let's call that the minima. So you get 2 maximas and 2 minimas. Right? So if you were to plot the H field, if I were to plot this H field, previously our HA of theta looked like this, where this was 2 pi. In this case, so this was for a 2-pole motor. In a 4-pole motor, it would complete a full curve in just pi angle. Right? Because this half a angle completion is a full motor in itself. We have a bunch of positive windings coming out, bunch of windings going in. That in itself is a complete motor. And if you look at the H field is peak here, goes to 0 here at 45 degree. Should have started it. So our H is cos of theta, right, not sine of theta. Right, so we start at one peak here at 45 degree, we get to the 0 at 90 degree, we get to the negative peak, and then 90 degree plus 45, 135, we get to the other 0, and then at 180 degree, we end up with a positive peak again. And then this again repeats once more. Okay. So this whole thing repeats again. Now, if I want to create a 6-pole motor, all I have to do is the same thing, but just compress this winding even further. Right? Instead of doing it over a spread of 180 degree, I do it over a spread of 120 degree. So 360 divided by the number of pole pairs that you have is the amount the positive and the negative winding pair would occupy in the motor depending on the number of poles that you want. Right? Well, when I go to higher pole motors, how many of you have worked with some kind of motors here? Either the EV project, the solar vehicle project. Does anybody here from solar vehicle project or the racing team? Right, Hannah? Lily, you're also part of it? Okay. So what is the advantage of going to higher poles? What will happen to the speed when we go to a higher pole? Let's start with that question. What will happen to the speed of the motor rotor when we go to higher poles?
Does it increase since we kind of increase the frequency of?
Okay. So let's say that's a very good answer. So let's say our frequency is 60 hertz. Right? In case of a 2-pole motor, let's say that omega comes out to some omega mech. So the question is, if I retain the same 60 hertz sine wave and I go to a 4-pole motor, what is the omega going to be? It should going to be definitely some constant times whatever the omega mech was in the previous case for a 2-pole motor case. Right? So Leo's answer is it's going to double. Right? That's a very good guess. Any other answers? So it actually does the opposite. It would be half of what will be in a 2-pole case. So there's an easy way to visualize this. So what happens is when, let's say we have this single pole motor. Let's say on the rotor, let's say I put a north pole here, south pole here. When the rotor completes one full rotation, if I look at the back EMF, my back EMF that we haven't derived the expression for back EMF yet, but bear with me. The back EMF in some sense would complete a one full sine wave, right? If I complete initially when it's north, it has some positive voltage, and as the north moves around and goes to the middle, the voltage would swap over, and then when we get the south pole, we'll get the opposite voltage, right? So that's what would happen. But now let's say I put a north-south, right? And I measure the back EMF in this case. So if this north goes to the top, the bottom south would come here, right? And then once this north goes to the other side, this, so let me call it N1, S1, N2, S2, S2. So when N1 goes here, S2 would come here, N2 would come here, right? And then when N1 goes full 180 degree, N2 would have come to the 0 position again. So within a half a cycle, the winding would have seen a full change from north, south, back to north, right? When we do a full cycle of the rotor magnet, what does it mean? That back EMF would also have done a complete cycle. But our full magnetic field of a rotor magnet just changed in half a cycle itself because we had 2 poles on the rotor. So our EMF would complete a full cycle in just half the time. And then the other half it will do another cycle. Right? What is our electrical frequency? Electrical frequency is same as whatever our EMF frequency is going to be. Right? So in this case, we had our omega mech same. And we saw for a 2-pole motor, if the frequency was F, for a 4-pole motor, the frequency would have been 4F for 4-pole versus 2-pole, right? But if I ask the opposite, if I keep the frequency same, what will happen to the speed? The speed would end up being half of what it was before, right? So the answer would be 1/2 times omega mech. Yep.
So to increase the number of poles, do you just change the winding, or do you have to change anything else as well?
You'll have to change the winding and you'll have to match the rotor poles to be the same as the stator windings. Right? If you don't have the thing the same, can you tell me what will happen? Let's say the stator windings creates 4-pole and the rotor magnets create a 6-pole. So whenever you have that kind of mismatch, go back to Fourier. Right, so if you look at our magnetic field in the air gap, if we have, let's say, go back to a simple case of a two-pole, we have sinusoidally created magnetic field in the air gap, and then the rotor is going to create its own sinusoidal magnetic field, which we'll get to later. The product of these two somehow interact to create the torque that we saw, right? And this product, basically the inner product, I shouldn't use the term inner product, I've introduced it, or taking the product of the two magnetic field and integrating it over the whole volume would give me the total energy and the torque associated with it and so on and so forth, right? Now, if the product of the two will, integral of the product of the two will only have a finite value if those two have the same frequency. If the frequency of one is different from the other, then the integral of that product would be zero over a full cycle. So if I have a sine wave in the air gap, magnetic field in the air gap, let's say, which is going as sine omega, sine of theta, let's say due to the stator winding, my magnetic field is looking like this. And due to my rotor magnets, let's say the magnetic field is looking like this. Right, 3 times. So let's say this is some time t, 1 by t, frequency 1 by t. This is some frequency 3 by t, right? Now, if I take the product of these two, it's the interaction of the two magnetic fields that create the product torque. And when we write the equation, you'll see that basically taking the product and integrating it in some form will give you the torque, right? So if I take these two products and integrate it, it's going to be zero. Unless these frequencies are exactly the same, the product integral would always be the zero. So the only case is that you will have to have the rotor magnet same as the stator magnets. Otherwise, all other combinations will give you zero net torque, right? Any other questions? Okay. Yep, Chris.
Why would you want to have like more poles if your speed decreases?
Excellent. Those of you from the solar vehicle project team, why do you all have like 10 poles, 20 pole motor? What is the purpose? What do we get? Torque. Under what condition will we get an increased torque? So let's say I have a motor with 50 turns, two-pole motor with 50 turns, and I go to a 4-pole motor with same number of turns, 50 turns total. Will the torque increase? No.
You need to increase the turns.
To how much?
Not sure.
Right. So the reason we do go to a higher pole count is because you can get more torque if you can increase the number of turns. All right. Let's see what limits the number of turns. So let's go back to our 2-pole case. Right. So in our 2-pole case, let's say our total windings is 50. Right. Where is the B field going to be maximum? At this point, right? The T is the point. Or in this point of the core where all the B fields. So we have a loop here, and there's some B field due to this loop. There is another B field there due to this loop. There is more B field, and so on and so forth. At this point, all the B fields add up due to all the loops. Okay? And this point, when you look at it, is where the B field in the air gap would be maximum, which will also mean the B field in the teeth would be at its maximum value at that point, right? So the limit of how many conductors you can put in this motor is going to be limited by how much B field is there at this point and how much B field is there at this point in the iron core. If the B field gets too large, then the motor goes into saturation, right? If the motor goes into saturation, then our motor starts to exhibit a lot of reluctance and it gets into a lot of losses, because if it goes into saturation, we're doing a big large VH curve. We are now in the domain of AC motors. So every time we do a cycle in our current, we are transitioning the whole BH curve, right? So we are going to have a huge amount of hysteresis losses. In addition to that, once the core starts to saturate, the air gap length, effective air gap length starts to increase, because the iron core now also starts to behave like air gap, right? It's no longer mu r equal to infinity. We cannot assume that there is no drop in the MMF in the iron core. There is going to be a significant amount of drop in the iron core. So that is what would limit. So the number of conductors that you can put in the core into the slots would be directly limited by what the maximum magnetic field is in this part of the yoke, as well as this part of the teeth of the stator. Now let's see what happens when we go to higher poles. So when we go to higher pole, let's go to the 4-pole case. So let's say this was the 3 winding, 9 winding, 12 winding, 12 winding, 9 winding, 3 winding. So for a total turn of 48 in this case, we are going to retain the same 48 turns in a 4-pole motor. All right, so let's see what do we have here. We have 6 here, 6 here, 12 here, for a total of 24. Again, another 24 here, another 24 here, and another 24 here. for a total of 96 conductors, same 96 conductors here. There was 48 here, 48 here, a total of 96 conductors. All right. So we are comparing the case where there is same number of conductors in a 2-pole motor and a 4-pole motor. Okay. What would have been the H here? At this point, what will be the H value? So if I do integral H dot dl, I would pick this particular loop, right? That's going to be equal to Ni. That is just going to be equal to 48 times I. So let's say this is Lg, this is Lg, that will be 2 Lg. So my H at that point where it's going to be the peak is going to be 48 I by 2 Lg in this particular case, right? And my B again is going to be mu naught times H. I should ensure that the B does not become too much that it oversaturates the teeth, that the teeth starts to add too much reluctance to the magnetic pathway. So let me go to the 4-pole case. The H will be maximum here. The loop that I'll take to compute that maximum H is going to be this loop. So if I go around, do integral H dot dl equal to Ni, what is my Ni going to be? 24I. Again, Lg on this side, Lg on this side. So 2 Lg, that will be the integral there. So 24I divided by 2 Lg, right? In the previous case, I had 48I divided by 2 Lg. In this case, I have 24I divided by 2 Lg. So in the previous case, let's say the H here was 1.2 Tesla at the teeth and it's saturated. What will be the H here at the teeth here for this case? What is it going to be? In the previous case, let's say H here was 1.2 Tesla. What will it be the H here? Half of it. So, sorry, I shouldn't have asked H, it's B. So here the B, let's say, was 1.2 Tesla. Here the B is going to be exactly half of it, 0.6 Tesla. Because my H got half. Mu naught times H is my B. So now what can I do? I can push the motor up to it gets to 1.2 Tesla. So I can pack in more conductors at this point. So now I can actually put, instead of 6 conductors, I can put 12 here, I can put 12 here, and I can put 24 conductors here for a total of 48 conductors. And here I can put again more conductor, 48 conductors. I can put 48 conductors here. I can put 48 conductors here, right? Now what happens is each of these conductors are carrying the same current as what it was doing before. I have more number of conductors carrying more amount of current, same amount of currents. So my Ni term is much larger than what it was in the previous case. Now this is going to interact with the rotor magnet, which again I'm going to size it so that it has the same magnetic field as the previous case, right? So this H field due to the rotor magnet, let's say, was 1.8 Tesla on this side, and then south the field's coming back in. I'm going to do the same here, north with 0.8 Tesla, south field coming back in, north with 0.8 Tesla, south field coming back in. So it's the same magnetic field interacting with a larger number of conductors carrying same amount of current. So what is the torque going to be? Torque is just the R times I cross B. So the number of current carrying conductors has increased. The magnetic field due to the rotor magnet is still the same. So my torque is going to increase, right? So it's somewhat of a misconception that if you just increase the pole count, your torque would increase. That's not the case. When you increase your pole count, what it allows you to do is it allows you to increase the current carrying conductors in your slots as well, because the peak magnetic field reduces. So you can double your magnetic field if you double your poles, double your conductor if you can double the poles. Since you double your conductors, you have double the amount of torque, so the torque increases in your motor. All right, so you can do either thing. You can either double the number of conductors and increase your torque, or you can reduce the thickness of your yoke. So previously we would have had to have some large thickness in the yoke because all the flux lines pass through this, and flux divided by the area is going to be a B. If the area is not large enough, your B field is going to saturate, B field is going to be quite large, motor will saturate, and the reluctance will be large. So your yoke height, your yoke thickness would have to be quite large. But if you go to higher poles, we saw that the B would have dropped down to 0.6. Right here, let's say it goes to 0.8. So your yoke length can be much smaller than what it was before. So you can make either trade-off. You can put more number of pole counts and reduce your yoke thickness and reduce the rotor thickness as well, make your motor smaller, or keep the same motor size, put more conductors and increase your torque in the motor, right? With it, let's call today and we'll continue next week.